Okay, folks, it's 5 o'clock, so let's get started with the 11th hour with your instructor. I thought that it would be a good opportunity to lower the anxiety and cover what material is going to be in the exam and things like that. Not that I'm going to give out questions about the exam, but rather to fine-tune you to what kind of material you should be focused in the last hours before the exam. I don't advise that you stay until late to try to remember everything, because you get don't get enough sleep, and the next day your performance is going to be not as much as you could do. You underperform, sort of speaking. So I suggested that tonight, at some point, you just stop doing that, because that's one thing that we call the law of the diminished returns. When we start getting better in the material, and that's a point that we start studying more and more, and we don't see an improvement. That's time to stop. And then relax. Tomorrow, take good meals and become very hydrated to the exam so that you can perform very well. So let's do like that. So I'm going to briefly recap the 5 letters that are part of the exam, okay? So we start with the welcome to BIS 102, lecture 1. It looks like a long time ago, but it was January 6th when we start. But half of this lecture was more like how can we do well in this class, and the ways and the means, and how this course, this is going to be delivered, the lecture is going to be delivered, and the material are going to be presented, and how we can do well in class and so forth, right? However, we focus on some material, and one of the material that we mentioned in class, and there was a question on Piazza, so at least one student have a little bit of a question about that. We talk about the structural organization of complex biomolecules. The goal here was to say, well, we're going to be studying proteins. Proteins are made of amino acids. Amino acids are the building blocks of proteins, and they come from metabolites. Metabolites come from precursors, and the precursors coming from the elements, which we have the periodic table of the elements, right? So what are these elements? We're talking about carbon, hydrogen, oxygen, sulfur, phosphorus, nitrogen. Those are the elements that are going to be in our protein, in our amino acids. And then these elements form molecules, form compounds sometimes, like H2O, and also form N2, for example, and the CO2 and so forth. So these molecules later, they incorporate, keep it going in the reaction, they make metabolites, and those metabolites generate, some of them generate building blocks. And we are not much interested in the building blocks on the right side, on the left side, the amino acids that we already started studying, but they are not going to be covered in this midterm one. Okay, so the goal here was to bring the idea and that notion that we are studying proteins, and it goes back where they're coming from. Okay, in that lecture also, I talk about the viruses, and if you notice that probably I have a little bit interest in virus, not because I'm a specialist in virus. I'm not a virologist. I don't study virus at all. The only thing I did with virus was when the Zika virus came as a problem in throughout the world. I studied together with collaborators in Brazil. I went to there because we didn't have the virus in here, and went to there to study how the virus affected the olfactory system of mosquitoes, and if the mosquitoes would be less sensitive to repellents. That is completely separated from those viruses here. That was the Zika virus. And the 2 viruses that I talked in class, it was very important for us that in the daily life, right? The SARS-CoV-2 that we show here, that they have these proteins on the surface that we call the spike protein. Therefore, that comes the name coronavirus, because it looks like a crown. So that's the spike protein. We also talk about the influenza virus. And we said, well, the influenza virus is a little bit different on the surface outside, because they have these 2 types of spike-like proteins, the hemagglutinin and the neuroamidase, HA and NA. And we talked that they have 17 types of HA, 10 types of NA, and the combination of these different types that give the name of a virus. For example, the bird flu is called H5N1 because it uses the type 5 of HA and the type 1 of neuraminidase. Hemagglutinin being important for having access to the host cell, and the neuraminidase is very important. Okay, so these spikes proteins are the ones that contact the host cell and recognize a receptor in our body, with the receptors in our body, they get entered to the cells and they hijack the cell and do all the work that they need to do. Here's a ChatGPT generated a cartoon of the comparison between SARS-CoV-2 and the influenza virus that I generated today, so that I don't want you to repeat the same pictures over and over, so I put a little bit different. So the difference that we see here from the outside is that they have different types of spike proteins, with the influenza virus having two different types, okay? And the coronavirus, the major part of the crown is only one is the so-called spike protein. And then we relate this to the properties of living entities. And we explain in class that despite of the fact that this virus kills so many people, they themselves are not living entities. And the classification for living entities is that they have to fulfill 4 criteria, and they do not fulfill 2 of the criteria on the bottom of this slide that we present in class. Well, they are very highly complicated, highly organized. You saw the structure, they're beautiful. They have a biological structure that serve a functional purpose. They have the RNA inside, protected, they have all these proteins and so forth. This is fine, but the 2 properties on the bottom, they do not fulfill. They do not actively transform energy. They have to hijack a cell to be able to do that. And also, they do not have a capacity for self-replication. They do replicate. If they didn't replicate, we didn't have a problem at all, right? But they do replicate, and a lot. But then once they hijack the cell, so they take control of the cell for their own benefit, and they replicate. And have the opportunity to have Dr. Charles Rice talking to class a week from tomorrow, and he's a famous virologist who discovered the hepatitis C virus. Anyhow, so in lecture 2, that was in January 8, we talk about bonds. And one of the bonds that we gave a lot of emphasis was hydrogen bonds. And we talk in class that these the hydrogen and oxygen from different molecules when close to each other. And there are other also parts of molecules like nitrogen and so forth. But we are focused here in this slide in water molecule. As I mentioned in the presentation yesterday, that was kind of a review that we did impromptu with the participation of 2 of your classmates, Alma and Jean. We talk a little bit about that, and I was thinking before that event, I was listening to NPR, and they were talking about the exploding trees in the Middle East of the country. Now we have a very cold weather, and I wish I didn't have prepared the exam because I would put that as a question for you to explain what's going on. So what is going on there basically is that water is because the temperature is too low, waters become solid, become ice, and inside of the trees, there's water, right? The solemn that's circulated in the tree, and the volume becomes so high that there is no space, and they crack the tree, and they call it the exploding trees, which is a very serious problem that's going on right now in some part of our nation. But back in here to the picture, we see here hydrogen, make hydrogen bond with the other molecule. If you look at the molecule in the center, we are going to see the hydrogen on the right side, make a hydrogen bond with the oxygen of the molecule at 4 o'clock. And also we had some other molecule like 8 o'clock, and there is a hydrogen forming bond there. You know that this molecule in the center there would be able to form 4 hydrogen bonds because they have 2 lonely pairs there that can make hydrogen bonds, and the picture here didn't include every single thing. I mentioned in class that sometimes I use ChatGPT, but to be very careful and try to, quote unquote, educate ChatGPT and try to correct things, but sometimes it doesn't work. We spend a lot of time. I spent a lot of time this morning trying to make this picture a little bit better, but they keep giving me this picture. And what's wrong with this picture? So I had to erase a part of it so that I would not be misleading, because this picture here is misleading. And I hope that you can write in the chat what you see wrong with this picture. I'm not going to check the chat in real time. I'm going to give this presentation. I go to check the chat. But here, it was a gross mistake that I keep telling ChatGPT, this is not what happened. And there is no such a thing as an oxygen-hydrogen bond, right? Hydrogen bond, by definition, there is a hydrogen involved in that, and there was no way that I could tell ChatGPT to connect the dot line that is about 11 o'clock. The dot line there should be the oxygen in the center, connect to the hydrogen, one of the hydrogen, not to oxygen, right? I hope that you know by now. And that's interesting that they keep doing the same mistake, and I keep trying until I gave up. And I'm not very easy to give up. We talk also about the hydrophobic interaction. We made it very clear these are not the bonds, but they are very important. They are a very strong interaction that drive the force of formation of the proteins that we're going to go back to that. And in this cartoon here that we addressed in class, we show that, well, the point is that no matter what, water molecules are going to be surrounded this fat material, right? So that's when they invade the water, intruding the water, there is going to be some sort of water molecule surround. So these water molecules that are surround are going to be trapped there. There's no other way. However, what the process is that we have to minimize this number of molecules that are surrounding the fat. And the way to achieve that is that when they come together, clasp together, the surface area, the total surface area decreased. Therefore, the number of molecules decrease. And then we explained this thing in class. That's, for example, here in the cartoon at the left side, we have 9 plus 8 molecules of water. And in the cartoon on the right, we see 11 molecules, so less organized water molecules. So no matter what, there is going to be some organized molecule. The point is to minimize the number of organized molecules. And we talk about that in another lecture from the viewpoint of entropy. We also talk these hydrogen bonds are very important because they are weak and strong to protect, for example, the code, the genetic code, and weak enough that we can easily access them. So these are bonds that are easy to break and easy to reform. So there's this properties of the hydrogen bonds that make them very important in biology. Lecture 3, that was January 13, we talk about the thermodynamics, and we talk about the first and second law of thermodynamics. And then we came with the Gibbs equation, the delta G equals delta H minus T delta S, where the delta G is the free energy of Gibbs, the overall energy that's going to be either available to do some work or is going to be required to do that reaction. So the process sometimes, I would not say produce energy, but I would say that, that the transform energy and the make energy available for other reactions to take place, for example. And sometimes some reaction needs the free energy for another reaction to take place. My metabolism going on as we speak now. For example, we are synthesizing new proteins, and synthesized protein is a very energetic, disfavorable process that requires energy to. So where this energy comes from other reaction that is yield free energy. So the delta G is the free energy of Gibbs. Delta H is the difference of enthalpy, and delta S is the difference of entropy. We give some particular names for delta S when delta H when it's negative. We call it an exothermic reaction. We talked about that yesterday as well. Delta H when it's positive is an endothermic reaction. And for delta G, we call the exergonic and endergonic reaction. A very important factor here is that we have to always look at the T in absolute temperature. We have to add 273 to the Celsius temperature. Forget about the Fahrenheit here. We don't use Fahrenheit in science, but we use Celsius a lot, and that is going to be necessary to transform that to get in absolute temperature, okay, in Kelvin. This graphic in here is another illustration. Like I said, I try to create something new so that I don't repeat myself with the same figures. This graphic in here shows a reaction that starts with a certain level of free energy, and the product has a lower level of free energy. Therefore, the delta G here is going to be negative because we are going to end up with a smaller number and subtract from a larger number. So it's going to be delta G negative. And delta G, again, is given by the equation that's underneath the graphic here, delta G equal delta H minus T delta S. And no matter what, whether the reaction is going to be exergonic or endergonic, the reaction is going to need the activation energy. That's the peak, but that's something that we're going to be talking more in the third module of this class when we talk about enzyme kinetics. We needed to know that there are such a thing, that there's a barrier in between the reactants and the products, and what they're looking at in terms of enthalpy of free energy of Gibbs is the difference between the two. We also walk you through, I'm not going to do that again here, but maybe you can remember practice again after that. We will walk you through this delta G called delta H minus T delta S. We gave a few examples and said, what if this is positive, this is negative, this is positive, this is negative, this is negative, negative. And then we analyze in various ways, including situations where the temperature is irrelevant, could it be high or low, or in cases where the temperature being high can give one direction, temperature being low, giving the opposite direction. So I encourage you, if you have time, to go over this picture again and try to reconstruct this graph one more time. That was not supposed to be like that one. We also talk about this hydrophobic interaction. This lecture, now that we introduced the concept of entropy, to give a little concept here that say, hey, look at this. We discussed this thing about the surface, the number of molecules. Now, look at that. If they collapse and make a single unit, the number of molecules organized are going to be small. So there is going to be more water that are going to regain the freedom. And the molecules that regain the field increase the entropy, right? Because if they are stuck there, they cannot move around. Molecules like to be moving around. So when they get stuck there on the surface, they are not be able, they don't have max flexibility to move around. So therefore, when they collapse, they move around and regain the freedom. And we talk about this Micelles formation and show that they form the same way here, except that now we have a polar head and the hydrophobic tail, and the hydrophobic tail gets in the center and the polar head gets outside. We talk about soap and what soap does and how do they allow us to get rid of greasy compounds in our hands and things like that. And also we talk about this in the surface of cells. We talk about the bilayers. The bilayers are exactly what we are seeing here. This hydrophobic effect allow the formation of these bilayers. Now we have a polar head outside, polar head inside of the cell. And in between, there is a region of hydrophobic material. So anything that has to pass through there has some difficulty and it needs to be, for example, we talk about that in class later on, I go back to that. We talk about in class molecules that are charged and non-charged, and we know that the molecules that are not charged, they have a little bit, it's a little bit easier for them to pass through the membrane than the molecules that are charged because they are polar and they do not dissolve well in fat, so they have time passing there. We talk about the relationship between delta G naught, which is delta G naught being the standard conditions, and delta G for non-standard condition at any conditions. There is a table for the delta G for a certain reaction. Delta G naught, we know for something for a certain reaction. But that reaction has to have a concentration of 1 for each material, starting material in the product, and be at certain condition, right? What about if I have the same reaction, but it's not the standard condition? Then I have a formula that is given delta G at any condition, include the modified biochemical condition that I talk about that in a minute. Delta G equals delta G naught plus RT logarithm of Q. And what's Q? Q is that we know the equilibrium constant, and we know how to make the formula of calculation the equilibrium constant. However, the equilibrium constant is only valid at equilibrium. And what about the reaction is not in equilibrium? We do the same calculation, but we call it differently. We call the quotient, the reaction quotient, Q. And then if I have the Q, I can calculate the delta G at that moment. I just need to know the temperature as well. Okay, and there are that in case of exams, the R is going to be given there. Can be given in calorie per mole. I never do problems in calorie per mole, but if you want to do that, that's fine with me. In equilibrium, there are two conditions that you know. In equilibrium, the delta G is 0, right? When the delta G is negative, the reaction is spontaneous. Delta G is 0, the reaction in equilibrium. And delta G larger than 0, the reaction is non-spontaneous in the direction that was written. In the opposite direction, is going to be spontaneous, right? Because all reactions depend the way that you write them. So now, another thing about the equilibrium is that Q is now became KQ. So let's plug in this number there like we did. And it's going to be very easy to come to this formula. Q is going to be now called KQ. Instead of log of Q there, we could KQ. Delta G, we put it there, the blue one would be 0. If you take 0 there, then we change the side of the term. Delta G naught equals minus, because it changed the side of the equation, right? Minus RT logarithm, not Q anymore, logarithm of KQ. That's the formula, and that's where this formula came from. And from there, if I know the equilibrium constant, I know the delta G naught. If I know the delta G naught, I know the equilibrium constant, and the relationship is like that. Pure algebra here that we did in class. If you know the equilibrium, the delta G naught, you can calculate the equilibrium constant for the reaction. In biochemical standard state, we don't use the concentration of protons equal 1. That's the only thing. Everything is the same, except the concentration of protons is not 1 molar like the chemists use concentration, right? So if we pick up a table that says delta G naught, we wanted to transform that in delta G naught prime. If the reaction has protons, then we have to calculate what's the delta G. Use this equation here. We have to calculate that, and we put the concentration of protons equal 10 to minus 7. Then we calculated that. If the reaction has no protons, and we don't need to do any calculation, delta G naught equal delta G naught prime. They are the same because there are no protons, so it's going to be no change there. Okay? Lecture 4, January 15, we talk about water dissociation. This is very important because the majority of the questions in the exam, and I already sent a note to remind you not to forget your calculator, okay? Because there are a lot of questions. We talk about water dissociation, we talk about water being a very weak acid, but water is still dissociate. It's very weak, but dissociate. And these protons that dissociate goes about Q of water and form hydronium, H3O. And another part of the molecule becomes OH minus because it lost a proton there. For all examples that we give, we always talk about water dissociating H plus and the OH minus. We know that the H plus is not exactly what happens in nature. In reality, it's hydronium, but it's make it much simpler for us to talk about the H plus. So we make this commitment moving forward, only talk about water that in equilibrium with H plus and OH minus. But in reality, what's forming is hydronium. We titrate material, so we know that when we have the same amount of acid and the base, that's when it's going to be neutralized. So we said, okay, the number of moles is given by M times V. So if I have the number of moles of acid and the base, M1V1 is going to be equal M2V2. In that case, in here, one could be a base and two could be acid and vice versa. Doesn't matter, right? Just the same thing. M1V1 equal M2V2. This is very nice, but there is a risk in here because this works well for monoprotic gas and monobasic substance, right? Or if they are the two of the same, diprotic and dibasic. If they're equal, there's no problem. So in order to avoid such problem, we decided that it's better to use normality, which is not very well defined in quantity, but we can easily calculate it because we have the molarity of the solution. We multiply by this K, and this K is based on being a monoprotic gas, K is 1, diprotic gas, K is 2, triprotic gas, K is 3, be a monobasic 1, dibasic, tribasic 3. So it's very simple. You just pick up the bond like, and then we don't run the risk of making mistakes. And now the number of equivalents being equal, then I call N1V1 equal N2V2. Okay, so if there's a problem of neutralization, that's the suggested the formula is N1V1 and N2V2. You might use the other one, but you have to be careful not to get trapped in any situation where we have a diprotic gas and be titrated by a monobasic or something or vice versa, okay? So watch out for that. When we introduce this concept, we also talk about the acid being strong and weak, and here the strong is based on dissociation, okay? Ionization, and some students ask me what's the difference of ionization, dissociation, same thing, different names for the same thing, synonyms. So we have an acid, and they are going to be dissociated. The more you dissociate, the stronger the acid is. And to make it simple, in class, I said, look at that. Look at, we have hydrochloric acid. It's so strong, dissociates so badly that almost everything is H plus and Cl minus. HCl molecules remains there, is nearly zero. So therefore, when we calculate the Ka, we don't even take it into consideration because the numbers would be so astronomical that it would be infinity, right? Now, look at the other side, a flip side of the coin. Water. Water is so weak that when we calculated that, it's so little that we even modify a little bit that constant of Ka for water. We modify and we call it Kw because I already incorporate water inside. Is 10 to the power of negative 4. Okay, so HCl would be infinity. Water would be 10 to the power of negative 4 or 14 or more than that because the Ka would be even larger than that. All right, so that's a two stream. So when you look at the NAS, you see that the stronger the higher the Ka, the stronger the acid is. Okay, and the pKa is an inverse relationship. If you are talking about the strong gas, a larger Ka, the pKa is going to be small because that's an inverse relationship, and the vice versa. If you talk about a very weak gas, then the pKa is going to be very low, let's say 10 to minus 10. And then we have the pKa is going to be 10, a very large number, okay? I'm sorry that the ChatGPT didn't put properly here. Ka should be H plus times concentration of A minus, right? And I don't know, hey, they put one additional bracket there that I'm not sure what. How you know that by now, and you know how to calculate the pKa as well. I never give in class the pKa. I always give the, I mean, in exams, I always give the Ka. So it's just one step, just the minus log of Ka, right? We have also in lecture 5, That's the last lecture that is going to be part of the exam. We talk about the various things, and this very, very, very important concept that you have to master that concept for us to move smoothly forward in the amino acids, okay? We have this concept that if I have a reaction, and this reaction here is deprotonating of this HX species, generate X minus. If I have that, I look at the center and say, this is my pKa. And if I move my pKa to the right, in other words, I have a pH above the pKa, the species on the right are going to be the predominant species. So if I go above the pKa, I would expect to have a high predominance of X minus and a low amount or a proportion of HX because I went above the pK. Yesterday, I even did some calculation to show how we calculated these numbers and we get the proportion, right? Now, if I am at the pKa equal, the pH equal pKa, then the two species are 50-50, okay? Equal amounts. Then I go to the left, I reduce the pH. If I go to the left, the species on the left is going to be the predominant species. In this cartoon that I present in class, I said, okay, I generated this picture here. It started with the flask on the left, where the pH equals pKa. So the number of balls represent HX and X minus, red and the blue, are equal in this flask here. Then I keep moving this to the right, and we see that the proportion of X minus decreasing. HX is increasing. The flask is becoming red and the red and the red, stronger red, rather than, and you see that they're very hardly to find any of the blue in the flask on the right. So what's happening here is that the pH is decreasing this direction below the pK. So I'm moving to the left of the reaction. If I move to the left of the reaction, HX increases, X minus decrease, the flask becomes red, the blue color is very difficult to find. Okay, so that's a very important concept for not only for the exam, but from now on. We talk about phosphoric acid. We can't do well in midterm one if you don't know things about phosphoric acid. Let me be blunt about that, okay? Phosphoric acid has various species, and we need to know which species at which point. We always look at that as a titration. We look at have a substance at very low pH, and then we start increasing pH. That's the way that we think about protein, amino acid, and everything from now on is like that. So let's start here with phosphoric acid at very low pH. At very low pH, phosphoric acid is predominantly the species on the left, which is H3PO4, because it's below the pKa 1, okay? Now, if I start increasing this pH by adding potassium hydroxide, for example, I see the left start decreasing and the species on the right start increasing. So you have a larger amount or proportion of H2PO4 minus and a decreasing amount of H3PO4. So if I look at this number here, this would be the pK1. That's the pH at which the concentration of H3PO4 equals the concentration of H2PO4 minus, which is also named dihydrogen phosphate. All right? Now, if I elect to keep going with this pH, increasing this pH, adding more sodium hydroxide or potassium hydroxide for that matter, now H2PO4 is going to start decreasing because it's going to be consumed by the addition of KOH, and the HPO4 started to be formed, HPO4 2 minus, monophosphate, monohydrogen phosphate. So the blue species monohydrogen phosphate is going to be increasing, and the species on the left, the green one, is going to be decreasing, and this is going to be the pKa2. And I keep going, and I do, again, one more step with the HPO4. I want to take the last proton from there. It's going to become a PO4 3 minus, and then we keep doing that and adding KOH, increase the pH, the species on the left start decreasing, and the species on the right start increasing, okay? I think the color here is not appropriate. The color here, the last trace should be gold. For some reason, didn't come out okay. But we get the point, right? And then I can ask you, what's the predominant species of phosphate? And the answer for that, I don't know. You didn't tell me the pH. If you tell me the pH, then I can tell what's the predominant species. For example, pH very low, the predominant species H3PO4. At pH very high, the predominant species PO4 3-, and everything in between. So then we have to determine which species. So depending on the pH that you are, we have different species, okay? So there are moments that we have 2 species equally. There are 3 different points. There are 3 different buffers here. So if you are not master this thing or not feel confident about this concept, go back and have a look at that, because this is very important, not only for tomorrow, but from now on, everything that we are going to be doing included there. Question that some people got a little bit uneasy about that. I talk about the histamine, I talk about other molecules as well. And I said, hey, histamine is a molecule that has this this group on the left side and this group on the right side that protonate and deprotonate, okay? So-called imidazole group on the left. And the group on the right is called the amine, or amine. So there is one place there in this nitrogen that they are almost at 12 o'clock, that hydrogen can be protonated. If you have enough protons in a solution, means low pH, that nitrogen is going to be protonated. It's going to get one more hydrogen, and it's going to be associated with 4 hydrogens, so therefore has to become positive, right? Same thing for the amino group. If you have enough protons there, this amino group can take 1 hydrogen and is already bound to 3, 2 hydrogen and 1 carbon there. If you put 1 more hydrogen, that will become positive. So this molecule can have 2 protons associated with that. So that's the same molecule. That's a different species now. And because I put this thing at a very low pH, this will be having both protons going to be there. That's how we think always about this problem. We start with a low pH. The pH, increase the pH, and I pass it to 5.8. When I arrive at 5.8, there will be 50% of the forget about the amino group. Amino group is not a part of the conversation yet, because amino group is 9.6, okay? So don't even think about that. There's this positive charge is going to be there. But if I have a 5.8 pH, is equal to pK1. So it means that 50% of the molecules, the imidazole group, 50% is going to be protonate, and the 50% is going to be deprotonate. I even asked in class, what's going to be the charge of this molecule? The charge of this molecule is not 1 from the amino group, is not 2 from the imidazole group, is 1.5, because only 50% of the imidazole group is protonated at 5.8. If I pass above 5.8, 1 or 2 units, let's say I'm at 7 or 8 or something like that, this all deprotonated, okay? So all, because I went above the pK a lot, so all this piece of deprotonated is going to be like this. Because I'm not there at 9.6 yet. If I go at 9.6 and pass that point, that will be deprotonated and become NH2. If I am at 9.6 exactly, 50% of the amino group is protonated and 50% is deprotonated, because this is the Henderson-Hausberg equation, right? That give pH equal pKa plus log of the concentration of the conjugated base divided by the concentration of the acid. if they both are at the same amount, that will cancel out log of 1, 0, pH equal pK. Okay, so what's the charge of histamine at 9 is 0.5. It's not 1, it's 0.5, right? So it can be 2, it can be 1.5, it can be 1, and it can be 0.5. It can never be negative because it's a base. It's never get, it's not like an acid. An acid gets lose, a proton becomes CO minus, become negative, right? This is a base. It's either positive or neutral, positive or neutral, positive or neutral. And then if there is more than one site, we analyze one of them at a time, okay? So for example, if I ask you, at the pH 7.4, what's the net charge of histamine? So all I have to do is say, okay, what's pH 7.4? It's between 9.8 and 9.6, 5.8 and 9.6, in between that. It already passed the 5.8, way past that number. So the imidazole group is completely deprotonated. And the amino group is entirely protonated because I'm not even there yet. So if I ask a question like that, the structure would be the second one from the bottom on the left side, right? Because that would be the imidazole group is deprotonated, but the amino group is still fully protonated, right? So that would be +1 in there. I could ask also the same question to say, put a proton or remove a proton from this structure here at pH 7.5, 7.4 in that case, or whatever pH I decide. So what you do here? Are you going to put a proton on the imidazole group here? No, because it's 7.4, 7.4 imidazole doesn't have proton. I'm going to put a proton in the amino group on the right side. Yes, because the 7.4 is way below 9.6. This amino group should be protonate. You add a proton there, put an H, and put a charge, because we cannot put a H without a charge, so it would be NH3 plus, right? So it's a simple thing, except that we need a little bit of critical thing to associate things that we learn with buffers to put it in real life, because we want the molecules to be deprotonated in this case, in this case of base. We want the molecules to be non-ionized so that they can pass through the membrane and do the actions and things like that, right? All right, so now I'm going to do one thing. I'm going to move to another part of the station here to see the chat and to see if there are questions there. So give me a second. I'm going to be moving to another place here. All right, so let me do that. All right, I see that there are lots of questions there. I hope that they didn't pass it through very quickly, because it's going to be hard to get back to them. Let's see what the questions are and see here. Hydrogen bonds need the hydrogen to be involved. Yes, it's phone. It's fluoride, oxygen, and nitrogen, and the hydrogen, right? So the nitrogen, fluoride is not important for us because we are not here dealing with inorganic chemists, but rather biochemists, right? Another question there, let's see, the protons, but it's hard because it was perhaps a question that was asked when I was presenting something. When there's a buffer, for example, the KOH or a wiki ASU, could you explain when to use the hundreds of basic? That's a very good question. Is the way that you look at that, we see whether there is a weak acid, and we add the KOH. So we need to figure out how much of the acid was dissociated or forced to dissociate, and it becomes the conjugated base. Then we figure out what's the concentration of the conjugated base and the concentration of the acid left. So now when I use Henderson as a bioequation, pH equal pKa plus log of the concentration of the conjugated base divided by the acid, right? Now I know this concentration. That's a very important way to do that. Look at the buffer like that. Let's see here. Let me, there's a double sound here. Okay, so first of all, strong gas completely dissociate. Yes, not necessarily completely dissociate, but they have a strong dissociation, right? That's correct. Does anyone have The Discord, that's something in between you guys. Uh, all right, so when deprotonate hydrogen at a low pH, when deprotonate hydrogen at low pH, do you deprotonate the hydrogen at a high pH value first? No, when we started the protonated, we start at a very low pH, right? So everything that can protonate is protonated. However, the ones with the lowest pKa's is the one that deprotonate first. I hope that during the presentation you figure out that part yourself. But if not, please go there and revisit that again. But we start with if there's two pKa's, right? Phosphoric acid, for example. The first one to deprotonate is pK1, right? The second one is pK2. So it starts deprotonated from the lowest pK, okay? So let's see here. Okay, so I think there's some question there. Are you being tested on this histamine example? Are you testing on something? I don't know if it's histamine itself. I'm not here with the same molecules, but that's the concept. The concept is there. You could be testing some molecule. I'm not going to repeat the same question that I presented here today, right? There, by coincidence, there could be something there. Especially if a question comes, I never deflect a question because I know that's going to be in the exam tomorrow. I always answer questions as they come. What chemical formulas do you have to have memorized, like citric acid, etc.? I think people are making a big deal about that, and I would not worry too much about that. Citric acid, we know the structure of citric acid by now, but I don't think that's a big problem to remember formulas and and the like. Okay, I would not worry too much. Uh, there's one question there. So if the pH is 10.6, the compound would be the one with no charge. I think it's someone is mentioned about the histamine, and that is true because the pH 10.6 is way above the 9.6. I think that was the largest pKa, right? So that's correct. And someone asked that also. Uh, so what's the N1V1 going to use it for? It's calculated volumes of buffer solution. No, not necessarily. This is more for neutralization. But that formula also, the M1V1, M2V2, works for dilutions. If the dilution is an issue, you can use that formula as well. The question is a little bit vague there. I'm not sure that I can answer that question. Can you explain more about the temperature effect on thermodynamics, please? I think it's in there in the equation, right? When you see the equation, the temperature about delta H minus T delta S could be the question. If that's the question, you have to analyze case by case. There are cases the temperature has no effect, right? Let's say that the reaction is exothermic, is increasing entropy, right? If the reaction is exothermic, delta H is negative. If it's increasing entropy, this is going to be delta H is going to be positive, right? Then the minus C delta S is going to be negative, delta H is going to be negative, no matter what, delta G is going to be negative, right? So it doesn't matter the temperature. But there are some other cases that they are, not quote me on that, but put it very simply, there are conflict interests, right? Delta H is going one way, delta S is going to another way. And so sometimes we have to account for the temperature because the temperature may change things one way or the other. It's included the example that I gave in class, a reaction that I said, okay, this gas in here are formed is spontaneous, but if you look at the different temperatures, they are no longer spontaneous. Can you show us how derive the Henderson-Hausberg equation by chance for clarification? Well, this would be not the best use of your time at this point to demonstrate the Hydrophobic equation. I never ask anyone to deduce equations in the exam. I ask them to know what the equations are. But it was a very simple calculation that I did in class, analyze the reaction and just doing some simple algebra that the Henderson and the Hausenbach did first. But at this point, the best thing to do is to remember what the equation is. pH equal pKa plus a logarithm of concentration of the conjugate base over the acid. And if it's POH, it's pKb that we use, right? How many questions are in the exam? There are 12 questions in the exam. They are not all the same weight, so therefore 12 are going to make 100 points because some questions are weight more than the other one. Can you explain when we will have to convert it to biochemistry standard state? Well, if there's protons involved, then we have to take that into consideration, right? So if protons involved, it does not work if you use delta G naught only. It has to be delta G naught prime. We have to remember glucose, right? Yeah, glucose, CH1206. You have to remember that for the rest of your life. Glucose is a very important compound. Are you able to do the exam in pencil? Yes, I said so, and but make sure that you write in strong letters so that therefore there is no way that the scan is not going to be good, because if you scan, you don't see that, that's going to be a problem, right? So it may put a little bit, some people like myself, I write very strong and things are becomes very clear, but some people write it which without much force and become a little bit light, so sometimes it's a problem with scanning. May you briefly explain when something is considered entropy driven? Entropy driven, enthalpy driven is that the delta G included both components, right? Enthalpy and entropy. Most of the reactions, the entropy are increasing, or a large number of reactions, entropy increasing. Some reactions, the entropy is decreasing, but the enthalpy is such a very important factor that weighs more the decrease of entropy. In that case, it's an enthalpy-driven reaction, okay? So that's when we say this factor is more important than the other factors. Uh, a very good question here. When doing a problem like what's the percent ionization of 1 molar, 0.1, I think, 0.1 molar pyruvic acid pH 3, how do you know that this is a buffer versus just an acid? That's a very important question, a very simple answer to that. If they give the pH, it's because someone adjusted the pH, especially if they gave a pH 3.00. No acid is going to be put in water and by themselves gives a pH of 3.00. It's going to be a pH, whatever the dissociation is going to be. And we know that when we put an acid in water, the way to calculate the pH is not by Henderson-Hausenbach equation, is by this business of making the concentration, like, for example, 0.1 minus x, and it gives x and the s, and find out what the x is, right? In this case in here, because they already said the pH is 3, that means this is a buffer. I start with this acid, I put some hydroxide or whatever, and it made the pH adjust to 3. Therefore, we knew exactly that was a buffer problem, okay? Are all amphoteric salt buffer solutions? Amphoteric salts, yesterday I gave a couple of examples. I strongly recommend, if you didn't the class, watch the video that I presented yesterday together with two of your classmates. And in there, I gave three different examples. When is a salt that we put in water, and there is basically no hydrolysis. Another one that when the salt was made of a strong, came from a strong base and a weak acid. And another one was when it generated an amphoteric species. That was something important. I don't know exactly which point of the video is there, but if you didn't watch the video, I would strongly recommend that you watch the video to review that part. Another question here. For a species distribution diagram like phosphate has, is the emphasis on identification dominant species at a given pH rather than write full equilibrium expressions? This is a very good question because we know that for the case of phosphoric acid, you need to know all these species, and you need to know, and I already said that in class and also in office hours, that you need to know how to write these three steps, right? Phosphoric acid, the protonation of the first proton, the second proton, and the third proton. You need to know this equation. And every time that you have a phosphoric acid, I strongly encourage that you write this thing first, okay? And then you can go and we solve the rest of the problem, okay? Will we need a control? No, there's no multiple choice questions. It's all open questions, and they're going to be, this is a good point about that, because even if you don't answer the whole question right, but if you know some, you get some credit for that. Yeah, so you won't ever give us a pH of acid solution of you, or will and want to be perfect value like. Now, what I'm saying is that by the fact that someone gave a pH of 3.00, it's clearly this pH was adjusted, because any acid that we have in nature, if you put them in water, which is it's not a buffer, it's just a solution of an acid, that solution there is never going to be a pH exactly 3.00 or 2.00, anything like that. No, there is no such compound in nature that I know of. Okay, so but the fact that the pH that was exact, it means that someone worked on that to adjust the pH. Okay, so let me go back in here and see if there are any more questions, and if not, let me see. All right, so thank you very much for watching, and I hope you have a good time tomorrow in the exam. So if you have been preparing well for the exam, I'm sure that this is going to be the case. Thank you very much. I think it's about 1 hour, so it should be time to stop and let you go. All right, thank you very much. See you today. See you tomorrow. Bye.